So for today's webinar, we are honored to have Mr. Seth Greenberg to present for us to discuss about constructability of curved steel top girder bridges. So Seth Greenberg, sorry about that. Yeah, is a structural engineer at Jacobs, New York, with experience in steel and concrete bridge design, advanced 3D structural analysis, on-site inspections, and design build projects, both in the United States and abroad. So he has experience in designing bridges and other transportation structures for various transportation agencies. Workload included like new bridges as well as modifications and repairs to existing ones. He also has experience like in inspecting highway bridges to assess the current condition and determine the scope of the repairs. Seth Greenberg is motivated to pursue professional growth and excited by opportunities to enhance the quality of our transportation networks. So now let's welcome him to present his webinar to us.
All right, thank you, Xiaofeng. Thank you for allowing me the opportunity to give this presentation today. I should be sharing my screen, correct?
Yes. I just gave it to you, the presenter.
Great. Showing up okay?
Yes, I can see it. It's all good.
Great. There we go. Again, thank you for the opportunity to speak today. I'm excited to talk about tub girder bridges, particularly because I think I've had a lot of experience developing a repertoire working this type of design. And I hope to give you all today a practical understanding of a lot of the literature that's out there about the subject, as well as different components of both analyzing and designing these types of bridges. So quick about me, I've been working on design build projects the last few years, and they're really exciting because they are often large capital projects, which have are put in the spotlight and get a lot of good public attention and PR. And one of the big advantages of the design build process is that we get to bring contractors early on into the engineering process so that we can design a bridge that is both easy to build and can be done quickly. And because we're talking specifically today about tub girders, it's worth noting that these types of complex bridges with complex geometries require a rigorous level of analysis. And that's because these aren't your typical cookie cutter bridges that you can design using some hand calculations. This has to be done, or is best done using 3D analysis so that we can get some of the complex nonlinear behaviors that you would expect. And when we design these types of bridges, we want to look for programs that can streamline the pre and post processing, as well as give comprehensible results. And because we're working in design build and we have constant coordination with the contractors, that we need to be able to make changes to the construction sequence or the structure in general very quickly and seamlessly. These projects, given that the expectation is that you can design it faster, you're often given a tighter schedule. So those are the demands we're looking to meet. Now for a quick agenda of what I'll be covering. I'll give a brief overview of why tub girders are advantageous and for what sort of structures. Then I'll review some representative projects I've worked on, which provide a framework for the rest of the discussion that we'll have today, talking about different functions within the program, as well as some design considerations that are specific. First, ask yourself, want to use. It boils down, I think, to be very efficient. That because they have a high torsional rigidity and because they can be fabricated with a high level of accuracy, they can follow any number of alignments and complex geometries like the ones shown in the photo. And I also want to emphasize with the efficiency that you can detail the curved girder bridges in a very streamlined fashion, because the geometry is very repeatable over the length of the bridge. You can design curved bridges using eye girders, either curved or straight, but when you're dealing with eye girders, what ends up happening oftentimes is that you have to have variable detailing over the length of the bridge, whether it's external bracing or deck overhang and the like, that you often have to have different details at different points in the spans or over the length of the bridge that requires a lot of extra detail that we want to be able to simplify. So the two projects I want to discuss today both happen to be in Australia. The first one is the Darlington upgrade in Adelaide. The project is a large grade separation in downtown Adelaide. And because of the complex geometry of both the roadway being carried as well as the main thoroughfare that it's going over, tub girders were very suitable for this project. One interesting note about the bridges built as part of this project is that they were moved into place using SPMTs, or self-propelled modular transports. That it's certainly a topic in and of itself that we can deliver a full presentation on, but I'm going to focus on some of the essential tools that were used in MIDAS to analyze and design the bridge. The second project is the Westgate Tunnel in Melbourne. That the tunnel itself is about 4 kilometers long, and at one of the entrances there is a large viaduct bypassing 2 major freeways. That the bridge itself is currently under construction. That the bridge piers you see rendered in the river area are under construction, and the steel superstructure is in fabrication. And I think what's really interesting about this particular bridge is that, given the incredibly long span lengths, we're actually pushing to the limits what we can achieve with this type of superstructure design. Quickly, I want to go over the general erection sequence for this bridge, the Westgate Tunnel, because I'll be making notes reference to it later on in different places. So just as a quick overview, that normally when we build girder bridges, they're built in a sort of straight line fashion, that you march from one end of the bridge to the other, erecting segments, and after that you pour the deck. But because we have this large river crossing in the middle, what we're actually doing is we're first directing the approaches on the east and west banks of the river, then filling in the central portion using floating crane, and only once that section is those 3 combined sections are stable, are we proceeding with the right half of the bridge that connects to Footscray Road, which is a separate structure. Now to go into some modeling objectives and nuances of different model types. In most finite element softwares, we think of girder bridges as girder or girder. The main distinction between the two is that finite elements are analyzed for motion. With the two-way action, you do get more information, but you can do quite a lot with just girders frame elements, and that's where we'll start. So firstly, the section properties that you would use for a tub girder element are pretty similar to a typical girder cross section, but the difference is that we want to be able to account for that torsional rigidity provided by the top flange truss in the stiffness of the member. And so MIDAS has adopted a fictitious plate method, which is an empirical method where you convert the truss into an equivalent plate, and that's used to create a pseudo box section for the purpose of analysis. And that provides significant resistance against warping. And you can also, in your section property, provide the concrete properties as well, both your short-term and your long-term behaviors. But if you want to get more specific, you can define your nonlinear concrete behaviors to be evaluated over the life of a construction sequence. And regardless of how you're defining your material properties, that when it comes time to actually make a construction sequence, you want to make sure that the deck elements are turned on at the appropriate stage using the composite section for construction stage feature in the program. Additionally, if you want to get very refined with your analysis, you can account for the rebar in the composite behavior. And this is particularly helpful when you're looking at negative moment regions of the bridge where your deck would be in tension. And because your deck is in tension, it's often a common analysis assumption to assume that your deck is cracked where anywhere on that surface is above zero tension. That different codes have different analysis preferences for that type of case. AASHTO, for those in the States, errs on the side of not cracking the deck, reason being that many of the design specifications used to check the girder members were developed assuming a fully composite deck with the girder. So we've got a case where we actually want to see how the composite action evolves over time. So this here is the proposed deck pour sequence for the Westgate tunnel bridges. Each one of these blue and white areas is a different step in the sequence, and the contractor is proposing that each one of these steps take place about every 7 days. And with that, given the number of steps and that specified amount of time, that the total deck pour sequence would take several months. And as a result, what ends up happening is that your modular ratio is actually going to vary because your modular ratio changes a lot in the early life of the bridge, that you're going to see a lot of nonlinear behavior. And so we wanted to be able to capture that. So using the nonlinear properties, we're able to get a more precise behavior of the bridge during erection. Secondly, I want to point out that against common convention, we're actually going to pour the blue regions first over the piers. And the reason being is that we want to provide additional torsional stiffness when the concrete is poured in the positive moment region. That the positive moment deck pour is what drives differential deflection between the tubs. And so we want to make sure our girders are as stiff as possible so that we have a nice, neat geometry once the erection is completed. That typically when you pour the negative moment regions first, you can expect some cracking in those regions. But because we are planning to pour a hot mix asphalt wearing surface over the deck once it's completed, we're not as concerned about detriment to the long-term surface life. Another feature worth pointing out is that many tub bridges use tapered girder sections, and both of the bridges I'm talking about today are using tapered sections. That MIDAS gives you the ability to calculate those intermediate section properties over the length of the taper. And I want to point out like a quick tip that MIDAS gives you the option that once you define your tapered group, you can turn each one of those sections into a unique section property. And while that may end up making your model look kind of clunky when you have hundreds of different section properties defined in your tree menu, it actually speeds up the analysis time. And while it may end up costing you time in the short run, because you have to set up all these different definitions, that you can actually set up programs in Excel. You can create tables and macros that can write each of these individual properties to Excel, such that when you analyze the bridge, they need to either reanalyze because of changes to the erection, design not being quite up to snuff. You can quickly make changes as needed. So now we'll talk about deck as frame. Because the longitudinal behavior of the deck is captured in the girder element, that all we're really looking at is the transverse behavior of the deck and those elements. And while these elements are very good at modeling the global behavior of the bridge, particularly the distribution of live load, they're not so good at capturing the local effects that you would expect for deck behavior. One reason being that the unbraced length of these elements is defined as the center line between the girder elements. And because these girder elements are defined center line to center line of the tub, you're deck span is actually longer than it would be in the field. And so what you end up doing is you get some fairly large transverse moments. And so while you may be tempted to design for these, you don't want to leave yourself, with extra, number 10 bars or something like that in the deck. That you want to produce a design that's conservative but sensible. That if you're looking to create a more reasonable design, you're best off either using the Ashton method or creating a local model of the deck. If you want to create a local model, you don't have to model the entire length of the bridge. You can usually just do the length make the deck span the length of your truck, and just run the truck over that to see how the live load varies over that length. Now we can talk about deck as plate. Deku plate elements do behave similarly in the transverse direction as Deku's frame, but because they're continuous along the length of the girder, we get much better localized behavior in the transverse direction. And also because in reality your deck acts more like a plate element than a beam element, that if you're defining nonlinear properties such as creep and shrinkage, you can better capture those effects over the course of the analysis. Though I wouldn't recommend that if you're looking into analyzing the effects of cracking over the negative moment region. It gets a little tricky if you try to do that with plate elements, because you want to be able to have the deck carry the live load transversely so that it's distributed properly between the girders. But you can't simply have your cake and eat it too. That if you're going to have non-composite behavior in the longitudinal direction, you're going to have non-composite behavior in the transverse direction as well. So it's something that it may not give you results that you would like to see. But sometimes we actually do want to take a closer look at what conditions under which the deck can crack. And for the Darlington upgrade project, I mentioned that we used SPMTs. And one of the key analyses we had to do before the moves took place was to figure out under what sort of relative displacement between our SPMT supports could we tolerate differential deflection between. And the reason being that we were particularly concerned about the cracking of the deck and affecting the long-term service life once the bridge was finally put in place. That over the course of the move, we had all sorts of strain gauges and monitoring equipment, so we can get live feedback of the deformations as things took place. And once things got into, like, we defined red, yellow, orange, thresholds. But once things got into like a little bit of a touchy area, the contractor would stop moving, readjust the supports, and keep things going. Now we can talk about girder as plate and deck as plate. That these types of models are very good for capturing localized effects, particularly if you want to look at things like bearing stiffeners, or if you want to do a global buckling analysis of the tub girders, if you have some non-conventional erection sequence, that you can get a more localized behavior of different loading cases. But one thing that is particularly useful for these types of models is calibrating the torsional behavior of your frame model. Reason being is that these plate elements more accurately capture the warping effects of the tub. That when you have a frame element, you define a single warping constant. But with the tub, not only are we modeling each discrete frame element, that we're actually able to also capture the out-of-plane deformation of the cross-section. So we're able to get, so with those increased deformations, you often see a relieving of those torsional stresses. And also, if you're looking to calibrate the global behavior of the model, you can use your sections for resultant forces feature so that you can select all of your elements that create a tub section at a specific point. And then using strain compatibility, the program can give you a summation of the forces in that plane. Once you model analyze those two behaviors, you can actually easily translate results from one type of model to the other using the section manager in the frame model. That you can just scale your torsional stiffness as shown by the results. And another thing I want to point out regarding the difference in behavior between girder as plate and girder as frame is the behavior of the external bracing elements. That typically, especially if you're dealing with eye girders, we often just model the external bracing from center line to center line of web. But we don't want to do that here, again, because of unbraced length issues, but also because if you want to create an offset like we show in this figure on the right, that you have these very rigid elements that are translating the force between the girders. When you have a Deku Plate model, you can see that there's actually going to be relative deformation across the width of the tub. That even if a tub is uniformly distributed, you're actually going to see different shear values, though only slightly different, between one web and another in the same tub. And so with that transverse effect, you're actually, proving that there's some deformation that takes place between the girder center line and the external brace that is not captured in the frame model. Now we can go over some of the construction staging functions in MIDAS. I want to start by going over Camber. Now, while Camber isn't necessarily the first thing you think about when you think constructability, I think it's an important tool within MIDAS to consider for curved steel tub girder bridges. One, because because these spans tend to be longer than other types of girder bridges, you want to be able to better capture those deformations over the course of erection. But also, there are some nice features in the program, but if they're not used properly, you can get some misleading results. So more broadly, the program gives you the option to compute deflections either as tangential or non-tangential. And what that means is, so by default, the program uses non-tangential displacement. And so as each girder segment is added in a model, it's placed at the initial position, at the zero deformation point that you would define pre-processing. So when it comes time to actually march through the sequence, in this particular picture, the bridge is constructed left to right, that if you have, as shown in this picture, you have an upward deflection at one girder overhang that, when the erection starts is like a cantilever, that in order to create compatibility with the new element, you end up with these kinks that distort your deflections, and that you often end up with local force hiccups at these kinks. That if you specify tangential displacement, what the program will do is it will, at the node where the two elements connect, that the new segment will be placed at that elevation, as well as parallel to the most adjacent framing member, so that you have a smoother parallel deformation curve. In the case of the Westgate Tunnel, as well as the Darlington upgrade project, we didn't have such a conventional erection sequence. One of the instances why is because we use temporary shoring, and as you'll see, that having temporary works of any kind has an effect on how the camber is computed. So in particular, temporary shoring keeps certain points that would normally deform downward in place at zero deflection during a temporary portion of the sequence. That the Westgate bridge is also going to be using access platforms at the splices. So that the way the erection sequence will work is before a new segment is lifted by a crane, an access platform will be attached to the end of that segment, so that when it comes time to splice the next segment after that, the construction workers can seamlessly move from one splice to the other. That it removes the downtime that you would normally have, like erecting a platform in the air. And these platforms are not trivial in weight because, as shown in this figure here, there's multiple levels to these platforms so that the workers can access both the top and bottom flange with relative ease. Because of how long this bridge is, there's a big emphasis on making the construction as efficient as possible so as not to have any idle time between steps. And so here's what a sequence like that looks like when it's analyzed in MIDAS. So in this first step, what we have is girder segments that are cantilevered over a pier. And then when a new segment is added, if you specify tangential displacement, it provides a nice smooth curve. But one thing you'll notice is that the deflection in the second stage at the point of the splice is less than in the first stage. And that makes sense if you're simply looking at the static analysis of that stage. That because it's changed from a cantilever to a continuous beam, that the deflection at that point is now less. However, over the course of the erection, there's actually going to be a point in time where the deformation of that splice that will still be 84 millimeters, what it shows in that first figure. And so what that means is that there's this intermediate case that we now need to account for. So what that means is what we've done is post-process these results so that we can interpolate between 2 points that we know the deformation of, but it's the deflection that's between those points that is not explicitly known in the program. So using the results of one stage and into the next, we can get a more refined camber curve. But one thing to look out for as you're using this feature is that you have to make sure to toggle all the right keys in the program because you'll notice that as the element is placed along that tangent curve, that you end up with non-zero deflections at a new support point. That all new nodes that are added in that step are plotted along that tangent so as to smooth out the curve. But you can see here that there's some fit up kinking, like similar we talked about with tangent, that needs to be resolved. We've actually had very helpful talks with MIDAS tech support to sort through this sort of behavior, and we're hoping that in future versions of the program that this can be addressed. Next, I want to talk about erection loading. There's a lot of good literature out there about the types of loading that you should consider when designing a bridge for all the different construction steps. And the things I really want to focus on for tub girders are wind, as well as construction live load. That for construction live load, because we're dealing with design build projects, they're sometimes willing to think outside the box when it comes to the construction sequence. So it's very much recommended that you work with the contractor to see what sorts of temporary works they plan to employ in order to make sure that all of the means that they want to use in the erection can be accommodated in the design. But for wind loads, it's important to know that because curved bridges are curved, that wind loads coming from different directions will control at different points at different steps of the sequence. So what that means is we have several wind load cases that we'll need to consider. AASHTO recommends looking at cases applied at 15-degree angles. And because previous versions of MIDAS capped the number of erection loads that you could use at 3, that we had to create separate models for each of the different erection cases and then post-process them in Excel to get a combined result. But after raising this to tech support and putting it on the ideas forum on the website, we were actually able to get a change incorporated in the 2020 version where we can now define a larger number of erection cases so that we can consider all sorts of different loading effects. Because you also, that if you're using certain combinations of temporary shoring, you also want to look at things like thermal and construction live load that you'll certainly find yourself looking at more than just 3 load cases oftentimes for these types of bridges. Now we can talk about some design considerations that are specific to tub girders. While we have lateral bridging like an obvious value to the design, what I want to make is that the bracing scheme provides specific.
Hi, Mr. Greenberg. Sorry for the interruption. Apologize for that, but I think your sound is a bit cut off. So can you repeat this part again? Thank you.
Okay. Can you hear me now?
Yeah, it worked right now.
Great.
Okay.
Right. So while we think of lateral bracing as a given for tub girders and an easy value added, that we want to make sure that the lateral bracing scheme that we provide meets certain specific design criteria. That because tub girders are often used for very long spans, they tend to be governed by buckling behavior as opposed to yielding. And so we want to make sure that those sorts of design checks are paid close attention to during analysis. And in one particular case with Westgate Tunnel, the contractor was very interested in removing temporary shoring as quickly as possible. In the particular case shown on the screen, temporary shorts are signified by the green circles, that these temporary supports were placed next to live traffic. So the contractor wanted to know, how soon can we remove these temporary supports such that the bridge remains stable? And what we have in this picture on the right is we have essentially this long, simple span with 2 relatively short cantilevers on either side. But because it's behaving like a simple span, we actually have a large positive moment effect at the center of the bridge, highlighted in red. And as a result, we actually had to, when we went back and looked at the numbers, we actually needed to increase the web thickness in this area so that web bend buckling will not be a controlling mode. And similarly, we also investigated the effects on the flange bracing because the spacing of your flange bracing is what controls your lateral torsional buckling capacity. And that's especially important in this span because you see that we have skewed supports. So any asymmetric loading applied at just the right magnitude can cause an uneven buckling sort of behavior. Additionally, as I mentioned, because we have this long, simple span that eventually becomes continuous, there's a point in time where the deflected shape is below the final shape, which is something we don't think of as happening very often when we construct girder bridges. So we also had to verify that the vertical clearance over live traffic was still adequate during this step. And so MIDAS has design modules which can check both constructability checks as well as key essential regular design checks that you would expect from a code like AASHTO. MIDAS also does compute checks for the Eurocode, as well as some other codes that if you look in the design features, you can check off. But it's important to note that it's very comprehensive, though it's certainly not complete, a complete analysis. And one particular reason why is because of if you're looking at a deck frame only model, that you're going to want to check for because it's a deck as frame model only that you can use these design modules for, that there are certain localized checks that you want to save for different model types. So to continue to the next slide, another thing that's important using the Camber output, which I discussed earlier in the presentation, is that we need to consider the fit condition as the construction staging advances for the purpose of detailing the cross bracing. Because of the as you get further out from the center line, you have increasing radius, and so your differential deflection between girders is nonlinear. And so what you'll want to make sure is that using the camber deflections computed at every step, you can actually provide the contractor with deflection data they can use to both detail and erect the external bracing at a given step. And it's definitely worthwhile early on in the process to pay close attention to your external bracing, because as the more robust your system is over the length of the bridge, you'll have less differential deflection, which reduces the likelihood of any fit-up issues you may have. And another thing that is worth noting when you're doing checks of design on tubs is like my programs check for
I'm sorry, Mr. Greenberg. It's lagging again. Can you repeat what you just say? Mr. Greenberg, can you hear me? I think your audio is still a little bit cut off. Hi, Mr. Greenberg, can you hear me? Excuse me, Mr. Greenberg. I'm sorry, everyone. So it seems maybe Mr. Greenberg, maybe a little bit of internet lagging. Let's wait him for a bit to see if he can get reconnected.
Okay. Can you hear me now?
Yeah, I can hear you right now.
Okay.
Can you repeat this part again? Sorry about that.
No, that's okay.
Thank you.
So while we may be tempted to shy away from buckling failure modes controlling our girder design, that it's worthwhile to consider the use of longitudinal stiffeners for your web and bottom flange elements, because you can save on the total steel weight used in the structure. But it's certainly worth weighing that against the fabrication cost. So it's not a hard and fast rule. And another thing to consider, which MIDAS does not account for explicitly, is the fatigue detailing that can be present at these stiffener locations. That oftentimes in tubs you'll have both longitudinal stiffeners and transverse stiffeners. That you want to detail the longitudinal stiffeners continuous and the transverse stiffeners be interrupted, similar to as shown in the figure, because fatigue is ultimately governed by the longitudinal flexure of the girder. So if we can minimize the number of disruptions that you see in the fabrication of that stiffener, you create fewer fatigue points. And now we can close with some lessons learned. MIDAS has a lot of really helpful features for modeling tub girder bridges at all stages of erection, from placement of erection to concrete pouring to final design. And they provide, a very good baseline to what is needed to turn an analysis into something that is buildable. Some of these features do require some pre and post processing by the user, but if these are set up early on in the process, they often can increase productivity in the long run. And the reason is because that you'll be very lucky if you find yourself completing a design, no issues at all on your first attempt. So it's good to set up your analysis in a way that's both easily repeatable as well as revisable, so that you can quickly, when changes are needed to be made, incorporate that and get the results and check the analysis feature you're looking for pretty seamlessly. Also, no program does everything. So it's important to understand in any program what the inner workings of the software are, so that you can improve the accuracy and the quality of the analysis that you're completing, as well as prepare yourself for any external analysis you'll need to do in a different piece of software. And lastly, it's worth pointing out that discussions with tech support can go well beyond just explaining how to use the help manual. That programs like MIDAS, which come out with new versions every year, are always looking to for ways to improve the software and provide a better user experience. So just because you think something is frustrating you now, it doesn't mean it can't frustrate. It doesn't mean it doesn't have to frustrate you forever. So definitely something to keep in mind as you encounter your own challenges on your own projects. I want to thank MIDAS for having the opportunity to speak today, and now I'll take questions.
All right, thanks so much. Thanks so much, Mr. Greenberg. So your presentation is really engaging, and also for the attendees and registrants, thank you so much. So apologize for a little bit like internet lagging. Thanks for your patience. Now you guys can input your questions here in the chat box, and I'm gonna address the question for Mr. Greenberg, and he will answer it for you. All right. So let's wait for their question. Okay. All right. Mr. Greenberg, can you see my screen right now?
Yes.
Okay, so here's the first 3 questions that I have here. Please answer them.
Yeah.
Thank you.
Yeah, I can go through them. Yeah. So could you explain the windload application for a constructability check? Did you make a separate model for construction state design with only non-composite members? So the first part of the question, for wind load application, that the wind load was applied as a separate load case within construction staging. And what the program can do is, while you can define your tub girders both as both the non-composite component as well as the composite component, you can use the construction staging composite section feature so that during a stage that if you're looking specifically at the wind effect, you can make sure that you're only looking at composite stiffness and related section properties. That for each step of the analysis, you can decide whether or not that bridge is composite in the model. So what that means is, for the purpose of actually checking the design, is that in the design module, you can actually use the construction stage loads as static load cases to be put into your load combinations. And what the program will then do is analyze all the load cases from that erection case over the course of the sequence, and then provide you the results for the government case. Next question, can you please comment on the redundancy of the twin tub girders? What type of stay-in-place form have you used? So as far as redundancy, right, that if you're dealing with eye girders that using a 2 girder system, is often not treated as redundant because you can't have a single eye girder support a lane of traffic. But with the tub girder, a two-tub girder bridge is not treated as non-redundant. One, because that the girders are much more torsionally rigid, and also many of the elements that make the bridge torsionally rigid are on the inside of the tub, which means they're, for the purpose of inspection, unlikely to be as deteriorated as say the external bracing of an eye girder member. Those internal bracing members are treated as primary if they are they're treated as primary when they're required to resist erection loading. But once the deck is composite, the bridge is redundant. At least that's my understanding. And as far as stay in place form, that for both of these projects, actually, we're using precast deck panels, which are then poured with a cast in place layer of concrete. So no additional formwork is required. The precast panels are dimensioned and casted, to preset sizes, and we have pockets inside the panels so that they can be fitted around the shear studs so that they remain composite once the system is finished. In the analysis, do you ignore a concrete deck at negative moment? Right, because going back to that slide, I can just have that on screen for comparison. Right, so while different codes treat this differently, in my experience, that the total change in moment can be roughly around 5%. That it's best to be internally consistent with whatever code you're designing the bridge for, and so therefore, whatever preference you have for analyzing the deck should be consistent with how you're designing the bridge. It's important to point out that while cracking the deck may decrease the negative moment at the pier, that does go to the midspan, increasing the positive moment. So while it may sound like you're actually getting something good out of it, you're actually creating a different problem elsewhere. So it's something to keep in mind. Any more questions?
Yes, let me show it to you. Just wait a bit. Let me address the question on the screen. Okay. All right, can you see it, Mr. Greenberg?
Yes, so what design checks are performed in MIDAS? I can go back to that slide quickly. Yeah, I may have gone a little fast through that slide.
Do you want to go over the slide to them again, with them again?
Yes.
I can give you the presenter mode. Yeah, sure.
Great.
Okay.
So the design module provides all the fundamental checks, mainly moment, shear, shear buckling, those sorts of things. And if you're defining it as a frame element, that the design module can use the predefined section geometry to compute your slenderness ratios, kind of what you see here on the screen to the left. That I provided a printout of the Excel report that you can get from the program, that for each element you design, you can have the option to print out a full in-depth report of all the design calculations that are computed, and it shows you every step that is used. And also, if you choose to have longitudinal stiffeners, it'll compute the the buckling capacities of those stiffeners as well, but it will not do any of the fatigue calculations. And also does a nice breakdown of short-term and long-term loading based on how you define your concrete material properties. So if you're looking to spell out, what forces are on the non-composite section, what forces are on the composite section, it can provide that for you. Okay, I think I can go to the next question. Is razor span length where you go to tubs or over eye girders? I think it depends on your L over R ratio. That's based on my understanding of the different literature out there. Is that if you have a high value of L over R, that means you have like a relatively tight radius. But if you have a large value of L over R, what that means is that your bridge is approximately straight. So that as your L over R gets bigger and bigger, your torsional effects get larger and larger. And that means that you'll want something that's more torsionally rigid. And I think that's a good tipping point. I don't have any numbers, but the NSBA document I referenced, like at least for the purposes of the fit up, they define some good ratios for what methods should be used for what type of geometry. Also, I think it really depends on span length. That one of the advantages of a tub girder over an eye girder is that you can make a really beefy bottom flange if that's what you need. That oftentimes if you have an eye girder, that your flange spacing your flange width can be controlled by buckling because it's an unbraced element. That a bottom flange of a tub girder is a braced element. So you can actually get much more bang for your buck in terms of bottom flange buckling capacity if you use a tub girder. Next question, do we get the FEM results? The results are just standard member stresses. Yeah, if you're looking at individual plate elements, you use the same results features. And if you create a resultant section based on different plate elements, there's a feature in the results section that if you go under beam loading, I believe that you have there's a section for forces on composite sections or something like that. I forget what the name of the exact wording is. But right there, if you create a beam section of resultant forces, that's actually found in the beam results, not the plate results. Do you use all types of models for each box girder bridge or only curved ones? I have found that different model types are needed when we find that the analysis that we've done for the fundamental design is leaves something lacking. That typically that I've looked at both for the most part, I've worked with both Deku, mostly using girder as frame elements, but I've compared analyses using Deku's plate and Deku's frame for different projects. That it really depends on what sort of analysis, what sort of behavior is or isn't being captured by the model. And also specifically that if your tub girder spacing gets, if you have variable spacing or if you have spacing that's particularly wide, that Deku's plate model may be more useful for the general design. But the trade-off is that you'll have to check the design using Excel. You won't be able to do that using the design module. So it's a trade-off. Are there any more questions?
Okay, let me address the last 3 questions for you. Just wait a bit. Let me put them. Okay. Oh, okay. Now Okay. Can you see it, Mr. Greenberg?
Yes.
Okay,
So did you find significant differences between torsional stiffness using equivalent plate versus as detailed 3D analysis? What I've found is that as far overall the torsional stiffness, this is going to sound scary, but you can be off by an order of magnitude. And while that may sound scary, that you're like if you then scale like that because your stiffness is relatively large, that your change in deformation once you scale up the stiffness in the frame model doesn't change a whole lot, but it does affect your bracing forces. That if you're worried about shear flow in the tub itself, that usually is not a governing behavior. But if you have let's say you have non-uniform bracing over the length of the tub, that in the areas where you have you transition from one spacing of braces to another, that the plate method, right, that it because it's based on an average, won't necessarily compute the it won't necessarily compute the brace forces at that transition point as well. But it's certainly within the right order of magnitude for the brace forces. It's more of a deformation issue that you'll find yourself looking at comparing frame models and plate models. Did you find for the long, simply supported spans, the system buckling effects began to control? Buckling of the entire system over the local flange, buckling between the brace points. Yes. So that in the case of that long, simply supported span, that web bend buckling was the controlling case over the other failure modes I cited. And web bend buckling is purely a function of the unbraced length. That it's not a function of your bracing or your span length. That it's based on like the vertical height of the web that is unbraced. So that in theory you could also provide more internal K bracing at the location to alleviate that behavior, but it's often much simpler from a detailing perspective to just make the elements bulkier. How do you select MIDAS silo take into account tensile deflections on CS? So I think there are some tutorials that go through step by step, but it usually, right, but it goes through, if I can share my screen, I had the window on the slide. That this construction stage analysis control data window has a lot of the features that you'll want to modify to get specific results over the course of a sequence. Specifically, if you want to activate tangent displacement, you'll see this initial tangent for CS box. And so you just check that off. And it gives you the option as well to do it for certain elements. That tangent for CS is only valid for frame elements, not plate elements. So I would be careful in terms of which model you apply it on. This lack of fit force control, I think that's based on the help manual. I think that's something specific to suspension bridges, or I guess cable stay also would fall under this category. That it's not something relevant for girder bridges. And also, that it gives the option to apply camber displacement to CS. That if you predefine camber displacements in your model, that when you get to the results, it can actually combine it for you. Whereas otherwise, what you do is that if you define a camber deflection, outside of MIDAS, that you would then have to export these results back out of MIDAS to get your final deflection to verify the camber you've calculated is equal to the deflection over the course of the sequence. Question?
That's it. That's it for consuming the timing. So that's it for the Q&A part for our for today's webinar. So the rest of the questions we will give to Mr. Greenberg and let him to answer it, and we can post it like in the review page. And thank you so much, Mr. Greenberg. We really appreciate your time today. Hi, Mr. Greenberg, can you hear me? Hi, Mr. Greenberg.
Great.
okay.
Yes, thanks again for the opportunity to present today. But hopefully next time we'll have fewer technical difficulties.
Yeah, sure. And also, like for all the attendees and the registrants today, thanks for joining our session. And so just to remind, like, so our session will be recorded and it will be posted on the review page. So Seth Greenberg is one of our expert influencer from MIDAS Expert Network. So it's a networking platform for engineers to learn from experts' experience and insights. So we have more than 60 expert engineers. They are proficient in MIDAS civil software. So if you are interested to like speak to Mr. Greenberg or other experts, you can join our expert network, and our representative will reach out to you and provide you the consultation or connect you to the expert based on your needs. All right, thank you so much. Thank you so much, everyone.
Take care.
Thanks so much. Thanks so much, Mr. Greenberg. Have a good day.